Thank you so much for the introduction, and welcome everyone. Good afternoon. Let me know if you I have a tendency to move while I talk, so if you can't hear me at some point, just let me know. So like you heard, I work primarily in machine learning for healthcare and NLP at Nuance, and I'm here to give you sort of a bird's eye view of this brand new hot off the press library for NLP deep learning work called GluonNLP. Just a quick show of hands, how many of you have ever heard of Apache MXNet framework? Just heard of it? Okay. Anyone who's actually used it? Anyone who works at Amazon, for example? Okay. Yeah, so I asked that because MXNet is what GluonNLP is based off of, and it's sort of a collaboration between Amazon and Microsoft, among other institutions. And if you work at Amazon, it's very likely you've come across it. So, what is GluonNLP? MXNet that you see right there is a scalable open source deep learning framework. And Gluon is sort of the imperative API to it. And the GluonNLP part of it is the high-level API focused on natural language processing. A corresponding layer to it is GluonCV, for example. So if you're interested in computer vision instead, that is what you would use. The idea is to provide very high-level API tasks for common NLP tasks. And there are plenty of other language bindings available. If you were at the morning session today at the keynote, and if Catherine managed to convert you, there is, for example, a Julia API available too. But by far, the Python interface is the most common one. So why do we need yet another framework? Because clearly, we don't have enough of those in the ecosystem, right? So there is constant talk of how much fragmentation there already is. There are all these famous frameworks that you've already heard of. Who wants to learn yet another one? The good part is that at least the Python binding of this should look very, very intuitive and familiar. So if you try and get your hands dirty with this, you'll realize that this is not so much this won't feel so much like learning a new thing altogether, but being able to do what you always do in NLP use cases, but with a lot more ease and flexibility. So a major motivation for this framework was reproducibility. And reproducing state-of-the-art results in NLP has been notoriously hard. Data processing is, if I dare say, especially messy for NLP and textual mode data. The sort of benchmarks that are released ever so often are based on data which is inherently messy, which is noisy, which is hard to clean, and the whole range of tasks that NLP use cases often offer are a big, huge mess. So if you've ever tried to reproduce results, those fabulous results that Google and Facebook come up with, good luck with that, trying to do with custom components. So especially in the language domain, there are lots of typical problems that you see in data handling. There are formatting errors. Unicode formatting is a well-known pain. Languages, just by their nature, follow very different grammatical and syntactic rules, and their representations differ from language to language. A very simple example, languages being read from left to right versus right to left. The data representation of it is just naturally different. Input padding is a reality in just about every use case that you can think of. And data handling is an unglamorous problem. Nobody wants to do data cleanup. You want nice and clean data to be handed over to you so that you can spend all your time doing fancy modeling. And that is what the aim here is. So that allows you fast prototyping, where we not only try to hand over clean data to you, but also a whole bunch of pre-trained models. Because while it's one thing to try and implement and learn about NLP by getting your hands dirty with toy example, the real fun stuff is really complicated and getting more and more so with time. So every time a new state-of-the-art benchmark is released, first of all, the complexity of it aside, the truth of the matter is that most of us simply do not have the kind of resources that go into generating these models up to the level of quality that the results need. For example, if any of you are like hands-on NLP people, you probably heard of this brand new model that Google released called BERT. And so BERT took about 700 to 900 days to train on the Google TPU cloud. So there is a huge value in being able to get pre-trained models for the purpose of inference, and sometimes it's simply beyond us to start from scratch. So a design principle GluonNLP sort of adheres to is to have high-level abstractions along with the low-level constructs like matrix factorization. So while you do have the ability to code a matrix factorization method if you want to, the basic units in NLP, which are commonplace in deep learning now, like things like, if you want to do batch normalization, while it might not be complicated to do so, it's sort of unnecessary to reinvent the wheel because it's sort of a standard procedure, and all you should really need to do is call batch norm. And again, a call back to Catherine's talk this morning. One thing I learned to point out from her today was that every time we say that X can do something, that shouldn't be construed as saying that X is the only one that can do something. So while a lot of these things are easy to do in GluonNLP, that is by no means to say that it's exclusively available only in this library. So this is a high-level API view of Gluon, and these are the basic building blocks of the NLP world here. And we'll look at some of the end-to-end examples, but data, vocabulary, embedding, modeling, loss, and initialization module for the modelings. The data API, mostly. So this is going back to the problem of the unglamorous part of deep learning, is that the primary aim here is to make data processing, data pre-processing efficient. So you need huge amounts of data to train neural networks, and the aim here is to provide useful abstractions to get textual data in exactly the form and shape required to train the deep learning models. One thing I would like to specifically point out here is the point about mini-batching and sampling that we'll touch upon briefly soon. One place that GluonNLP shines is that a lot of effort has gone into providing a number of popular benchmark data sets out of the box. So you basically need to literally just call these by names without having to worry about doing any pre-processing, any cleanup on it, and using your own models or using any of the pre-trained models. It is really simple out of the box to run an end-to-end method. So this is by no means an exhaustive list, but for example, the Google 1 billion word level formats is the standard for all language modeling tasks. The analogy and the analogy test sets are the benchmark for evaluating all kinds of word embeddings. Wikitext 2, 103, they are basically just various versions of the Wikipedia word level data set. Similarly, all of these are machine translation benchmarks. Quad right there at the end is is the benchmark associated with the state-of-the-art question answering system from Stanford, also known as reading comprehension. That link there basically will give you the list of all popular benchmarks available. So going back to data batching, to train our models, it's not sufficient to just have the data. It must both be in a right format and efficiently arranged for computation. So this usually means that in the neural network world, you need to group the data together in batches so that it can be processed in parallel, getting the best use out of the available resources, mostly GPUs. So for efficient training, you need to transform the input data into what we call mini batches, and consider a model that takes independent sentences as input. So this part is the simple transformation of the input data. And in any kind of data set that you can imagine, it's very unlikely to have inputs of standard constant length. So your sentences in every data set differ. If your units are paragraphs, their lengths differ, document lengths differ. At whatever granularity you talk about, the input units are almost always of different sizes. For example, this is the first 100 paragraphs from the Wikitext2 dataset that we talked about, and this is the distribution of how their lengths vary. Now, what this means is that data padding comes into play in a way that you need to basically make sure each of your batches is of a constant size, and to do that, you pad each of the smaller inputs to make it to the maximum input length. Normally, this is left up to the user, adding a bit to his or her cognitive load. And your input samples, when they are of varied length, the padding has to be made to maximum length, and with no bucketing, we'll come to how this is actually done in GluonNLP in a second. But in the absence of any sort of bucketing, if you simply just divide your data at random or in serial order or whatever, the average padding for each of these mini batches is about 11.7. This is the number for the Wikitext2 distribution that we just saw. And what this means is this makes data loading slow because there's an inherent memory inefficiency here. And the mini batching is basically related to parameter updates. So this is a fairly common operation and a frequent one. What GluonNLP provides out of the box is something called sorted bucketing. So instead of just creating random buckets and letting the padding do its thing per bucket, you divide it into n samples each and then sort all of these buckets. And that way your padding basically looks like this. So you're trying to basically group similar length sentences together, so each of your mini batch level padding becomes less and less, which basically just makes your loading much, much more efficient. The average padding in this case, if you see right there, is 3.7 as opposed to 11.7 in the previous case. So this is something that is straight out of the sampler class in GluonNLP, and this literally has technically no coding involved. Coming to the model API, in any NLP task or any statistical modeling task in general, this is broadly the standard flow. You gather data, you build your model, you train the model over the data, you evaluate it, and you infer on unseen data. This is a very, very broad view. A lot of these steps might be iterative, and this is just to outline how let's say a typical use case would look like. We'll look at one right away. So one of the most basic NLP tasks is what we call language modeling. And we will just look at what it takes to create a language, basically to use a language model in GluonNLP. So a statistical model is simply a probability distribution. It's over sequences of words or characters. We'll look at the word level language modeling here. And what this gives you an answer to is which among the following strings that you're about to encounter is more likely to appear in a language. So a perfectly grammatical sentence will have a high probability of occurrence, while incoherent babble of words put together, even if it might be grammatical, will have a very low probability of occurrence in a particular language model. So it basically tries to assign precise probabilities to each string of words. So what that means is that given a sequence of words, the job of the language model is to predict the next one at every time step. In the neural network world, this is broadly what the structure might look like. You have input words, which map to input embeddings. Again, if you've worked with NLP, you're probably aware of word-to-vec sort of embeddings or GLOVE embeddings or fast text more recently. And then the hidden state layer here is where the magic lies. So this could basically be any kind of deep learning model that we talk about. For language modeling, the most common one known to be used these days is what we call the RNNs. And one of the more common examples in GluonNLP is the LSTM model, which is the long short-term memory model, which is a specific kind of RNN model available. So this is pretty much what it looks like to generate a language model in GluonNLP. This is the basic setup, all of it very familiar, standard imperative Python code. This basically sets up the context. If you have GPUs available, by all means, go ahead, use them. If not, you can fall back on the CPU setup here. This is how you set hyperparameters. We will see how they are used in the training call much later. If all of these variables should be, by and large, quite familiar. This is the batch size, the learning rate, the number of epochs. That is probably too low, except for demo purposes. The BPTT is the backpropagation through time parameter used in the batchify call that we'll just see, and the gradient clipping numbers. Again, if you're wondering how do you know how to set these numbers, that is where the black magic of deep learning is, to be honest. And each of these parameters literally is a paper each, and still with no good answers. So these numbers, if you're wondering, are largely empirical and come from experience, so to speak. So this is how we can load a data set, extract a vocabulary, numericalize, and batchify for the truncated backpropagation through time method. This is the Wikitext to data set that's being loaded here, and the partitioning into train, validation, and test systems. The BPTT thing is not something that you want to get hung over. It basically just transforms the data set, the corpus BPTT batchify method. It transforms the data set into batches of numericalized samples, and in a way that the recurrent sets basically from the last batch connect to the current batch for each sample. So, and then there are a whole bunch of arguments associated with that. And this is how you can load a predefined two-layer LSTM language model with the tied embeddings and the output weights. So the function call is literally just this. And if you print the model and the vocabulary details, this basically tells you what is the model that you're getting. This is basically telling you both the embeddings and the hidden dimensions are about 200, and the dataset name on which the pre-trained model is trained. If specified, then you will get the returned vocabulary from the training set of the dataset. And the dropout values, the embedding dimensions, and the whole 9 yards. This is how you set the parameters for the trainer. This is where we utilize the value of the learning rate that we set earlier, and we specify our loss function, which is the standard softmax cross entropy. And this is what it takes to train the existing model. Our loss function here is the cross entropy loss used for the multi-class classification. And in this case, we'll backpropagate for 35 time steps, which is the value we set for BPTT right at the start, updating our weights by SGD, which we specified here, and a learning rate of 20. That was one line of training, and this is one line of evaluation. This is where the test loss comes from. And the evaluate method basically returns the test loss, and that is where we calculate the perplexity from. The perplexity is the standard way of evaluating how good your language model is. Essentially, minimizing perplexity can be seen as maximizing the probability. So less perplexity makes for a better model. So in this case, for example, the Wikitext 2 system that was loaded has a test perplexity of about 170.49, which is fairly good, empirically speaking. So this was basically about 20 lines of code to get the state-of-the-art LSTM language model. On the other side of the spectrum is another NLP task, which has been considered the holy grail of NLP for a long time, which is machine translation. September 2016 is when Google set up the system called the Neural Machine Translation, which is the GNMT system now. And they replaced their previous statistical method with this after about 10 years. And this, at this point, supports about 100 language pairs. And this is pretty much the first time where this level of transfer learning was successful, where we could see zero-shot translations being made, which essentially means that even if you trained your system to translate between, say, Japanese and English and Korean and English, your system was learning how to translate between Japanese and Korean as well. So this was pretty much never done before. And this is the data from the side-by-side evaluation that Google had released. So the neural GNMT system comes fairly close to the human system for a lot of language pairs. This is the architecture that was utilized to generate this state-of-the-art system. What this is showing you right now is an encoder-decoder architecture. The network here is basically encoding the source words as a list of vectors, where each of the vectors is the meaning of the words that it has encountered so far. And once an entire sentence is read, the English sentence, the target language, is generated one word at a time. And the decoder basically pays attention to the weighted distribution of the source vectors. So the details of this architecture aside, the point of putting this diagram here is to basically just get a consensus that this network is freaking complex. And if you wanted to reproduce these numbers or, generate this model, so to speak, would be hard, would be complicated, would be error-prone, and again, the point about how much resources actually go into generating a state-of-the-art model. So a model like this is available out of the box. So this is literally all that is required to construct the GNMT system. You can call the GNMT encoder and decoder by the get GNMT encoder decoder, and with the parameters that either come by default, or again, this is available for tuning. And then you can feed the decoder and the encoder to the NMT model to construct precisely the model that we saw. The Google model is also open source, and it's a TensorFlow models, which means that their numbers are available and available for reproduction as well. And the GluonNLP team did reproduce those numbers. And this is the blue score that they have on that. So blue score is the standard way of measuring translation systems. And this is the standard numbers that Google released. And these are the numbers that GluonNLP has with pretty much similar parameters. A huge improvement on this was in 2017, which is the famous transformer system, where, again, without going into too much detail of the architecture itself, still a fairly complicated architecture. The point of this was to demonstrate that you probably don't even need LSTMs. What you really need is a standard feed-forward network, and the key is really in attention. The paper that this came from is literally called "Attention is all you need." And again, point being, still a fairly complicated system to generate from scratch. Again, available right out of the box, and these are the numbers, in comparison with the TensorFlow implementation of the same thing. This is an English to German translation system. Again, this dataset publicly available and included in the library. I do want to go back for a second to the GNMT system and point out this particular line where it says model.hybridize, and I want to dwell upon that for just a second. So the hybridize part of this, to basically talk about what hybridize is doing there is to draw your attention to the difference between the deep learning programming paradigms between the different frameworks, for example. So again, this is not a very watertight kind of demarcation, but by and large, very broadly speaking, there are declarative frameworks and then there are imperative frameworks in the ecosystem at the moment. So with the declarative frameworks, or what we call the symbolic frameworks as well, these are TensorFlow, for example, Theano is another one. What you end up doing there is to declare a fixed computational graph, is to construct a fixed computational graph first, and then execute it end to end. Now, once your computational graph is fixed, that basically means it's portable, it runs more efficiently, it can be preloaded, and what that also means is that you are trading off some flexibility because you can't really you can't really encode any special logic in there like you can in, say, an imperative system like NumPy, for example, very, very simply speaking. So while it also makes a preloaded computational graph much harder to debug because it's hard to manipulate anything that's going on in the intermediate states of that. But because of its efficiency, TensorFlow, Theano, some of the big frameworks in the space are actually declarative in nature. The imperative frameworks, on the other hand, are also well represented by some other big frameworks, PyTorch, Chainer, for example, and GluonNLP at the moment. They are just the opposite. They execute commands one by one, just like you would expect in the normal Python control flow, for example, what you see in NumPy or in MATLAB, for example. It's everything that the symbolic systems are not. It's slightly easier to debug. It's slightly easier to interrupt and inspect. It's more flexible, but at the same time, it makes it less efficient for precisely the same reasons. Now, what GluonNLP tries to do here is to hybridize. It tries to get a hybrid execution. So the block construct in Gluon is basically the base class for all kinds of models that you create. The sequential construct is is sort of the basic neural network layer object. So it stores a chain of neural network layers that execute in turn, where the output from the previous layer becomes the input of the next layer. So everything like this, for example, would be a sequential object, or something like this, where you see neural network layers stacked on top of each other is basically an implementation of sequential layer. Now, the sequential construct is basically right here. The sequential construct is the base class for this, and to be able to create a hybrid symbolic and imperative system, what GluonNLP does is it implements a hybrid block and a hybrid sequential class. So the idea behind that is to, one second, is when you call the hybridize method on a model, what it is trying to do is to basically allow for creating a symbolic graph in the sense that it is going to make imperative calls, but after the activation, the first hybrid forward call that you make, the symbolic graph is basically cached. So it gives you the ability to get the efficiency associated with with preloading an existing computational graph. So the next time you're making a forward call within the neural network, it is not going to make an explicit function call, but it is just going to preload the cached computational graph. So it sort of gives you, the flexibility of the imperative paradigm, as well as tries to utilize the efficiency associated with the symbolic paradigm as well. So by default, within MXNet, everything that's pre-designed is in terms of hybrid sequential. So if you basically went back and inspected the NMT model here, you would see that it would be constructed out of hybrid sequential blocks and not just sequential blocks. Which essentially also means that if you're creating a neural network of only MXNet layers, you don't really have to worry about this optimization, and it comes built in, which is sort of a nice segue to the last point I'm trying to make, that if you are, for any reason, really, really invested into one of these paradigms, that I really love PyTorch, don't make me move to GluonNLP, there is a way to not fight and peacefully coexist, which is ONNX. And ONNX is the Open Neural Network Exchange format, and it's an open format to represent deep learning models. It's a sort of an intermediate representation which supports all of these pretty well-known frameworks. And it's easier to move models and convert them from one framework to another. And this is right now in the MXNet contrib.onnx package. And the format supports MXNet in one direction right now, which means that if you have a model created in, say, PyTorch or any of the frameworks that it supports, it's easy to import it into MXNet Gluon directly, and it can be used with the optimized inference engine within MXNet, even if your model was not trained within the same framework. The opposite direction is not available right now, so you can't really export an MXNet model right now, but I saw at least one place where it says that it's in the works and might be coming soon. So this basically just increases the flexibility of using models that might not be available in MXNet world or in GluonNLP right away, or if you've created a model which is, really high performing, but it's all written in PyTorch. You don't really have to sit and rewrite it in GluonNLP. It can be directly imported due to the ONX support. These are the references, the best-known references for GluonNLP. They do have a couple of forums as well. I think the existing forum is probably all in Chinese, and the English help forums have sort of moved by consensus to Stack Overflow. So, but the Stack Overflow support is amazing for GluonNLP. The GitHub repository is obviously useful. The documentation, if you do check it out, notice the section where it says example scripts. So it not only provides pre-trained models for you to load, there are full end-to-end examples for a whole range of NLP tasks, the sentiment analysis, translation, which basically need a lot of building blocks to come together, but there are a whole range of example scripts available that are easy to run straight out of the box. That's pretty much it. And be happy to take questions. I am, if you find me outside in the hallway, ask me what I did with this, which is not much at the moment. This is really, really new. But I have tried my hand at using the existing use cases, and the only trouble is that a lot of these are heavily GPU dependent. So you can see how they work end-to-end pretty much in a local environment, local CPU-driven environment as well. To see the actual numbers that they report, unfortunately, you will probably need a GPU environment. So, thank you.
Thank you, Sneha. Does anybody have any questions? We can take like one or two. Yeah.
You mentioned that it had some ways of helping you get things in the right format. Does that include, like, for a given model to have like a text normalization pipeline that gears it towards like the same that they used for training that particular model? Because I've heard that can be, very impactful to make sure you're normalizing the text in the same way that, however, the model was trained as.
Do you mean the pre-existing data sets in it, are they normalized for use out of the box, or do you mean you want to...
For new data that you...
For new data that you bring in? Yes. So there is the data pipeline API in general. It has... what I'd suggest is look up what the data stream abstractions are. So there are a whole range of data stream abstractions which basically just let you sequentially call transform methods on it. So you can essentially just load any kind of data and run call successive transform methods on it.
Great, thanks.
All right, thank you so much, Sneha.